Hello students, welcome to the next lecture of the group theory. Today we will discuss some definitions of groups. We will discuss groupoid, semigroup and monoid. We had already seen what is a group and what are the operations that can be performed on the group. We had already discussed about the properties of the groups and we had talked about the abelian group. So let's see what we mean by a groupoid. So by the definition, if you will see, any algebraic structure, that is algebraic structure with some set S and with some operation asterisk, if this algebraic structure is closed with the operation asterisk, so closed with the operation, then it will be called as a groupoid. So any such structure that is S comma asterisk which is closed with the operation asterisk, that is called as a groupoid. Let's talk about for example of groupoid. Let's say if we'll take the set of all positive integers with the operation plus. So this means set of all positive integer and the operation is plus. So will it be closed with the operation plus? Yes, it will be closed, because for any two elements of the set of positive integers, if we'll apply the operation on these two elements, then the resultant will also be a positive integer. That means it will lie in the set. For example, if we'll take 1 and 2, the two elements, and apply the operation plus onto them, then it will be 1 plus 2 will give you a 3. 3 also stands in the positive integer set. So in this way, this will be a groupoid. So now let's talk about the next algebraic structure will be called a semigroup. For being a semigroup, it should follow the two conditions. One, the binary operation has to be closed operation, as we had already talked into the groupoid, and the binary operation is also an associative operation. So this is another property of the group. We had already seen the associative property, that is if you can see here the associative mathematical version of the associative property, a asterisk within the bracket b asterisk c should be equal to asterisk b asterisk c. So we can also take the same example with the positive integers and the operation as plus. So if we'll take the three elements 1, 2 and 3, so if we'll say 1 plus 2 plus 3, either we'll say 1 plus 2 plus 3 or we'll say 1 plus 2 plus 3. So in the association result, the result will always be 6. In both the operation it will be similar. So we'll say that that will be a semi-group also. Let's talk about the third definition, which is of a monoid. So monoid has three properties. One, it has to be a closed, the operation has to be a closed operation like in the groupoid as well as in the semigroup. The operation has to be associative operation like into the semigroup, and there will be the existence of an identity element. So this is the another law, that the existence of an identity element. So what we mean by identity element? The element on which if we perform operation with any other element, the resultant with the same element. So that is the you can also see the mathematical representation of this identity element. There must exist the identity element in the set S for which this E asterisk A or A asterisk E should be equal to A for all A that belongs to S. Now let's take the example. If we'll add this into the positive integer, if we'll start this set with 0, so we have 0 as an identity element, because if we'll sum 0 with any element, the resultant will always be that element. So if we'll sum 0 plus 2, the result will be 2. If we'll sum 0 plus 10, the result will be 10. So 0 is behaving as the identity element. So that kind of set with the operation plus will be a monoid operation. Let's see some examples also. If n be a set of natural numbers, then n with the plus is the groupoid, as I have already told you. With the plus operation, the set of natural numbers is also a groupoid, and that is closed under addition. But let's say what is not a groupoid. If the set of odd integers, let's say the set of odd integers odd integers, that means 3, 5, 7. So if we'll plus 3 with 5, then the resultant with 8, the result will be 8, and 8 will not belong to the set of odd integers. So for example, 3 plus 3, the result is 6. 6 is not an odd integer, so this will not be a groupoid because it is not closed under the addition operation. So this is not a groupoid. If Z be a set of all integers, then Z plus and Z dot are semigroup because these two operations are associative. Then the third, the set of positive integers and asterisk is the operation of LCM, will the operation of LCM, then this is a semigroup. It is also commutative. So semigroup, we will have the existence of the identity also. In this also we can say Z plus, we have the existence of the identity, and even Z dot, in this also, in both these we have the identities. In Z plus we have 0, and in Z dot we have 1 as the identity. If we multiply any element with 1, the resultant will that particular element. So these are the groupoids, monoids and semigroup we have talked in this lecture. Let's say a semigroup, a theorem. Let's talk about a theorem. A semigroup S comma asterisk is a group if and only if there exists an element in S such that E asterisk A is A for all A in S. That is the existence of the identity. If in a semigroup the identity exists, and for all A that belongs to S and B that belongs to S, B cross A is also E. So if these two properties follow, then the semigroup will be a group. So these two property has to be followed for that. For the proving, we can say that, let's say S comma asterisk is a semigroup and that satisfy both the operations. Then for B that belongs to S, such that C cross B will belongs to E. We have taken the assumptions that there are two elements, B and C. For that C cross B will be equal to E. In that case, we will see the A can be written, if we are assuming that E exists into this, so this will be equal, and we had replaced this C cross B cross A with this, and finally C cross E results. So A asterisk B is equal to C asterisk E identity, then asterisk B, C asterisk E asterisk B, C asterisk B will be equal to identity element. Now A asterisk B, this is identity, B asterisk A, also A asterisk E, and this will also conclude. So we can see that just by assuming we have proved that there will exist the identity element into the set, and we also have inverse of every element. So that was the second property of the inverse, that there must be inverse exist for every element. So now this will be a group, the semigroup will be a group. That's it for the lecture. In the next lecture we will talk about some more examples and some more definitions of the group theory. Thank you so much.